Thank you. Thanks. Okay, good. So good morning, everyone. Yes, so I'd like to talk about topological crystalline insulators. That's going to be for 3 lectures all today. Before I actually get to that subject, since the introduction to topological insulators itself has been rather brief so far in the school, the first lecture this morning will be actually on topological phases in the very conventional sense again. And in particular, I'll basically connect to what Ivo did yesterday and talk about the Wilson loop characterization of topological phases. So this is a very, I think, convenient standpoint to understand bulk boundary correspondence and the bulk topological character of topological insulators. The second lecture will be about topological crystalline insulators in the more conventional sense. They've been discovered or thought about since 2011, 2012, and so that will be basically covered there. These ideas, or actually the ideas range even further back. And the third lecture today will be about a rather recent development, which goes under the name of higher order topological insulators. And these are systems that have been discussed only in the last few months, but they are also topological crystalline insulators. So in that sense, it all fits together. It's just a sort of an extension of the concept, if you wish. Okay, so again, if you have questions at any time, please interrupt me. As with all the previous speakers, that's important to slow me down and to make sure you follow along. Okay, so let's start with Wilson loops. This has a little bit of overlap with what Ivo did yesterday, but good morning, Andre. But this time I'll do, just to have the complete theory there, the non-abelian case, which is nothing that should scare you. It just means that we are not talking about a single occupied band, but we are talking about a number, say M, of occupied bands, and the indices that I'll use for them is M and N. And then we have Bloch states, if we have a translational invariant crystal, U, K, M. And out of these Bloch states, I'll form the yep. No, you don't need to be sorry for interrupting. Yes, that's a good point. There will be lecture notes latex, but it will take a little bit. So if you want to have it right now, you take your notes, but in a few weeks, or let's say months to be generous, you'll have them uploaded somewhere. Okay, good comment. Now the non-abelian Berry curvature is a vector that we call A, and it has indices M and N, and it has a momentum dependence K, and it's just the derivative, basically, the K derivative on the nth band, and you dot this, or you sandwich this with the mth band eigenstate at the same K. Notice that I didn't put that I here that Ivo put before. That is purely for pedagogical purposes. You know, just to be a bit inconsistent, that's what you encounter all the time in the literature, so you should just be prepared for that. So now we can form the Wilson loop, and the Wilson loop is simply along a path L is the path-ordered exponential of the integral of this Berry curvature, and now you note that this path ordering, because we have this non-abelian Berry curvature, is really important. So this A being now a matrix in this formula, you cannot just integrate it and then take the exponential, but you have to path order. So that guy is now also a matrix, right? So this W is an M by M matrix. That depends on the path L. Okay? And again, numerically, you can compute that as well. And what you would do is basically you would take, so to get the NM matrix element of this guy, you take the N state here. Then you take a projector, let me call it P twiddle of K. Then you take P twiddle of K, at K plus delta, and so on. And then you have P twiddle, let's say, I'll just write K plus 2 pi just to make sure you have to go in some closed path, but it doesn't need to be, of course, by closing it with 2 pi. And then take the mth band. And this P twiddle really is just the sum over all occupied bands, U, K, N, U, K, N. Okay, so the projector on these bands. And so now you see that this quantity is not gauge invariant, right? You see that if you change the basis, because this non-abelian construction, it's actually gauge covariant, right? It will change by the gauge transformation that you apply to this outer part. But what is important is that the spectrum of this W is gauge invariant. Okay, so we can think of the spectrum as something that we can look at, and it should contain some physical information about the system that we study. So one thing that I would just, so then basically the important thing is now how we choose the path, right? And we had already two choices basically yesterday, right? If you choose a path that's just, in some higher dimensional parameter space or in some K space, some circle of sorts, then you would call this a Berry phase. If you choose a path that's basically wrapping around the Brillouin zone, sometimes it's more called a Zuck phase. And that is the case that we want to study. So in the following, we will choose L to be along the Kx direction, spanning once around the full Brillouin zone. Okay? And yes?
Can I ask a basic question?
Sure.
As a non-abelian nature comes along, that yesterday we learned about the abelian nature.
Okay, so the non-abelianness is what it's a fancy word, but it really means that this is a matrix now. So we have multiple bands, right? Multiple occupied bands. And then the point is that this doesn't commute at different momenta anymore, these matrices here, right? So yesterday we had one occupied band. It was just a number. We can integrate. It's done. But now this is non-abelian, meaning non-commuting, because this matrix changes and is as a function of... no, yeah, the bands have different energy, but that's kind of mostly irrelevant from the point of view of topology. So we think of an insulator as basically dividing our Hilbert space, our single particle Hilbert space, in two parts, occupied and empty. But what the sort of detailed energetics in the say occupied part is basically irrelevant. Everything is occupied, so it's kind of the same for us.
What was the line above exponential derivation?
Above the yeah. So that's just for path ordered, so that you remember that you have to do path ordered exponential. Yes, if you only take the U1, yes, that's right. So what she's saying is that if you have only diagonal gauge transformations where you don't mix the occupied bands. So, for example, if they are not degenerate, that would be kind of a physical thing to do. Then it's gauge invariant. That's right. But in general, I want all capital M gauge transformations. Right. Very good. Keep on firing questions. Okay. So now I want to look at for the rest of the lecture, I want to look at the path in the x direction, a path that's wrapping all the way around the Brillouin zone. And then I'll, just as a notational subtlety, you see that I underlined my k. That's something I usually don't like to do, because now I'll write k vector as of here, and that is ky, kz, depending on the dimensionality. So everything but kx. Okay, when you see vectors now, it means that. And kx is kind of out of the game because I integrate over it. Okay, good. Just for notation. Okay, so now I want to provide you with proof for a statement that also Ivo made already yesterday. That is about the connection between this Wilson loop and the position operator, or the eigenvalues of the position operator, which is, you know, these Wannier charge centers. And for that, I'll erase. I hope you're somewhere writing. Okay, so what I want to do is, this is meant to be, I want to show the spectral equivalence between the operator minus I over 2 pi times the logarithm of W of k. And you see now I label my W by these momenta, which are perpendicular to the direction in which I integrate. Okay, so these are all sort of good quantum numbers, or, you know, parameters for my Wilson loop. And an operator P of k x P of k, which is the position operator projected into the occupied bands. So the position operator in x direction. And this P of k is defined as sum over n and here I have Bloch. These are Bloch eigenstates, so they're all orthogonal for all the k's. And I'm integrating over kx only. Okay, because that is basically the set of states, right, that the x position operator can mix. Yeah? So these are, I still have the good quantum numbers ky, kz, and so forth for this operator, but the x quantum number will be shuffled by the x position operator. Okay, so let's just write the eigenvalue equation for this operator, and we'll see where we get. So P of k x P of k. I'll call these eigenvalues theta of k over 2 pi, and then an eigen function psi of k, and that's supposed to be 0. Okay, so this is just the eigenvalue equation, and then an ansatz for this function. Well, what could what can we expand in? We can expand in the Bloch states at this given momenta. So, okay, maybe I should be more clear. This is a big psi here. And let's call the expansion coefficients just f of k and n. They are for all these bands. And then the basis would be the Bloch states k and n. Okay. So okay. So now I can take this state, apply it to the operator and take a matrix element with any of these Bloch states and see what I get. So the point is, so I take the Bloch state at k and n. And now my claim is that you get the following. You get I times partial f of k and n partial k x, and that's the function of kx, plus I times the non-abelian Berry curvature element at k. Okay, and maybe a way to see this, why this happens is, so you can rewrite the x position operator, you can rewrite it as, say, I times partial k x, right? And then what I basically have to compute here, so these projectors, they don't do much because this is already a Bloch state in the occupied bands. So then basically what I have to compute is sum over m dk tilde. Let me say this is a k tilde because it's in the sum of here. Then I have to compute something like this. Okay, well, this k tilde is now basically kx tilde, but then ky and kz they don't need a tilde, they're the same as on the other side. Okay, so and now what we see is that this partial kx tilde, it can either act on this guy, okay, and then we get this term, or it can act on this guy, okay, and this is a Bloch wave. And now it can either, so the Bloch wave, I'll just motivate this a little bit. So the Bloch wave would be e to the I kx tilde times x times, well, actually it's like k tilde times like the position r, okay, times du k tilde m, yeah. That would be this Bloch wave. And so when it acts on this guy, it will bring down the position. But once I integrate over the position, if it acts on this guy, yeah. Once I integrate over the position, I'll get rid of this factor. And the other part, when it acts on this u, will give me exactly the non-abelian Berry curvature, right? So that's where it's coming out. Yeah? Yes. But only the ky, kz, right? Yeah. So I want to show basically that this operator has the same spectrum as this guy. So I haven't yet actually involved this one, okay? So I only want to talk about this operator at the moment, but we'll see now basically that this is connected to the Wilson loop. Okay, so we haven't yet talked about the Wilson loop, and so now basically what you see is that this equation here, if you plug it or this thing here, yeah. So that's meant to go in here. And then for the f, you have a first order differential equation that, actually I think I forgot the f, right? Yes? Actually I forgot the f here. That is the x direction, yes. Yeah, it carries an index x. And that should be m, and that should be kx. Sorry, I forgot that part. Of course, that's left over right here. So because the derivative is in the x direction, it's the x component, so it doesn't depend on the coordinate x, right? It's just the x direction. So now we see this is a linear differential. Now we see that it is a linear differential equation in F, and so we can just exponentiate the rest if we want, right? Or so integrate. So here is the derivative. And so we take all the rest to the other side. And what you find then if you do this is that f of k and n of kx is equal to e to the minus I. And then so we have to define where we start our integration. And let's say we start the integration at kx equal to 0, kx 0. And then it's that times theta of k over 2 pi. So that is kind of an abelian factor that I can just integrate, right? This is from here. And then I have the rest is this path-ordered non-abelian integral that I can basically only write, okay, let me, times sum over m exponential path-ordered from k naught, kx naught to kx, some dkx tilde of ax of kx tilde k. Okay, and of this path ordered thing, this is now a matrix, this exponential, I take the component n m, okay? And then this has to be, times f m, f k m. Okay, so now you almost see what's happening is if we now take this integral around the whole loop in k space, so from kx equal to 0 to 2 pi, for example, but I could have also started at some other kx 0, then over here we have exactly the Wilson loop. So these f states are also eigenstates of the Wilson loop operator, right? And so we can basically write it as sum over m w of k and m f k and m, and then I can choose, for example, I can integrate from minus pi to pi or something like that, and then I get whatever the k0 is here, and this is equal to e to the I theta of k f of k and n of pi, for example. Or I could have written k0 here. This may be better. Okay? kx0. So the 2 pi basically, since I integrate once around the circle, the 2 pi cancels here, and all I get is this this theta. Okay? So now the question is, so this seems to relate to the eigenvalues of the Wilson loop somehow, right? So this is an eigenvalue equation for the Wilson loop. So this e to the I theta of k is an eigenvalue of the Wilson loop. Now maybe I should have left exactly that equation. Okay, so we looked at the eigenvalues of this operator, right? So we called them theta of k over 2 pi. And now we relate them to the Wilson loop eigenvalues, which are e to the I theta of k. Now my question is, if I have m bands and I have L unit cells, how many eigenvalues does the Wilson loop have, and how many eigenvalues does this operator have? Okay? M occupied bands, huh? So if I have M occupied bands and L unit cells, how many eigenvalues does the Wilson loop have? The Wilson loop operator. That is not too hard of a question for you. You're just too tired. M times what was N again? So, okay, then you wanted me to use N unit cells instead of L. Okay, so M, L, okay, fine. So what has how many eigenvalues? So the Wilson loop was a matrix, right? How large was that matrix? M cross M. So how many eigenvalues does an M cross M matrix have? It has M eigenvalues, right? So, okay, so W has M eigenvalues. And I'll call them E, and they are E to the I, and of course they depend on K, and let's say, let's call them J, right? Okay, so these are the eigenvalues. And PXP, now how many eigenvalues does that one have? It's the position operator, right? So if I have L unit cells, so L is there, but there's also this extra thing that actually I have multiple Wannier states because I have multiple occupied bands, right? Each occupied band is kind of giving me one Wannier state in the counting. So this has M times L eigenvalues, right? So, but wait, here I have theta. So these eigenvalues are theta k j over 2 pi. So I'm missing something, namely the factor of L. And the factor of L comes in because this relation here, of course, is only valid modulo 2 pi, right? So I can shift the position operator eigenvalue by 1 unit cell, and the Wilson loop eigenvalue won't notice because it's in the exponential. So I can add to this guy an x, and then call these eigenvalues maybe theta kj x over 2 pi or something like this. So these are the eigenvalues. So in this axis element integer, these are the eigenvalues of the position operator. So the position operator spectrum is basically a repetition of the spectrum of the Wilson loop with integer spacing, okay? So if the Wilson loop has, so I say I have these unit cells, right? And the Wilson loop maybe has 2 eigenvalues, one here and one here. Then that's the spectrum of the Wilson loop, or the logarithm of it. And then the position operator means that I have these Wannier centers each time, in each unit cell, right? Okay, it's time for an example, I think, to reduce the confusion a little bit. And the example that is rather canonical in 1D is that of a 1D chain with a dimerized hopping, or with a alternating hopping. So let's make an example. And that's the 1D chain. Okay, and so I want to have atoms, and I think of spinless electrons as hopping on these atoms, and I have each time I have a strong bond and a weak bond, a strong bond and a weak bond, and the weak bond is coming with a T hopping integral, the strong bond, or 2 different bonds, let's say, they can also be the other way around, is T prime. And then, so the two atoms in the unit cell, I'll call A and B, choose it like this, okay? And it continues. So the Hamiltonian that describes that thing is I'll just give you the Bloch Hamiltonian. I hope that you're fluent in translating between real space and momentum space. So there's no term in this Hamiltonian that is on site that connects an orbital A and orbital A again, right? So there's 0 on the diagonal and also here. So I don't want to put any chemical potential or anything, and also there's no hopping between A and A side, right? Here comes another A, here B, so it's always off diagonal. And then within the unit cell, I have a hopping between A and B, okay? And that hopping is of strength T. So I'll put a T here, and then to make it Hermitian, I put a T here as well. And then outside of the unit cell, I can hop with a T prime from B to A. So I'll write T prime times e to the I k, okay, my one-dimensional momentum. And then to make it Hermitian here, there's T prime times e to the minus I k, okay? So are we happy with this Hamiltonian? This describes this physical situation. So now that system has an inversion symmetry, okay? And the inversion symmetry, so what is the inversion symmetry? It's the thing that, so for example, here in the middle of this bond, basically I have two choices, right? I can make an inversion symmetry with respect to this point or with respect to the boundary of the Brillouin zone. Let's say we choose this here. So it changes A and B, right? So the inversion will map A to B and B to A. And of course it sends K to minus K, right? So the inversion will be some unitary matrix that connects H of K and H of minus K. So what is that unitary matrix? So very good, sigma x. Okay, so that's the inversion symmetry. Okay. And then there is another symmetry which makes this thing the Su-Schriefer-Heger model. And that is the so-called chiral symmetry. Now you heard about this Wield Wiest, which is actually not a symmetry, from Alex already yesterday, and that was sort of a bit dubious. And it remains dubious, but it's a mathematical fact that I can find an operator C. Okay, let me write down here, chiral symmetry. That I can find an operator C such that H of K for every K is mapped to minus H of K. Okay, so I'll change, so this is spectral symmetry for that, because if I have an eigenvalue at energy E, then applying C to the corresponding eigenfunction gives me an eigenstate at minus E. And this operator is sigma 3 in this case. So C equals to sigma 3, right? So you see that sigma 3 doesn't appear in the Hamiltonian, and for that reason, it's anti-commuting, right? So this is only sigma 1 and sigma 2 if you expand it. And so this will serve as a chiral symmetry. Okay, so that's just a statement for now. We'll use these symmetries just in a moment. But before doing so, let's just calculate this bloody Wilson loop now in a simple case, right? And the simple case that I want to look at is t equal to 0 and t prime equal to, say, 1 or whatever, to t prime. So why can I do that? Well, I haven't yet actually told you what the spectrum of this thing is. So what we can quickly maybe think about it. So if t is equal to t prime, that is just describing hopping on a chain, right? With no special features. It's translational invariant, right? Then I guess you would know that this is a cosine band, right? That describes the hopping. So this is a gapless point, right? If t is equal to t prime. Now, if I switch on a little difference between t and t prime, well, first of all, I cannot look in this units in this Brillouin zone anymore because the translational symmetry is basically reduced, right? And I have to look into this Brillouin zone, and then I have to fold over these outer parts, and I get a band that looks in principle like this. And then the difference between t and t prime will lead to hybridization between these two bands, and the spectrum will look something like this generically. Okay, so this is for t not equal to t prime. So I have an insulator whenever t is not equal to t prime, and the metal when t is equal to t prime. So there's some sort of phase transition at t equal to t prime. And so then once I have an insulator, I can, since we are interested in topology and so on, I can sort of go to a convenient limit. Here is a very convenient one, because basically this hopping here is switched off, and only the one between the unit cells is on. So in this case, the two eigenstates of the Hamiltonian, well, first of all, the eigenvalues are plus and minus 1, and the eigenstates are 1 over root 2 times e to the ik and 1, and then I have the eigenvalue minus 1, where I have 1 over root 2 times minus e to the ik and 1. And now let's pick that lower band, compute the Berry, now this is abelian, of course, the Berry phase, or the Berry connection. It is I over 2. So this 2 is important, right? It comes from the fact that, I have a wave function that's sort of equal weight on two sides, and only one of them depends on k, if you wish, right? That's how it comes about, if you take the derivative. And now it's easy to calculate the Wilson loop. Or let me just calculate minus I over 2 pi times the logarithm of w, which is minus I over 2 pi times the integral of a of k. Now that a of k doesn't even depend on k, so that is just 1/2, okay? So we see that in this limit, we get 1/2. And that is basically for t less than t prime. Now what would happen for t larger than t prime? There we can go to the limit where, for example, t prime is 0, and then the Hamiltonian doesn't depend on k, and hence there cannot be any Berry connection. And so immediately we can compute that this Wilson loop will be 0 in this limit, okay? So we can see that for t less than t prime, we have 1/2. For t larger than t prime, we have 0. Now you can be suspicious and say, well, maybe that 1/2 or something that has to do with your special limit that you took, right? I mean, I went to take this t equal to 0 limit. But actually, one can show that because of the inversion symmetry, this quantization is enforced. So inversion symmetry, what does it do to this Wilson loop? It reverses the path along which I integrate, right? And so let's say it reverses the k path in the Wilson loop. And hence, what it does, it generically is it will take your Wilson loop eigenvalue theta of k, and now this is the k with the arrow, and this is an equation that's more that goes beyond one dimension. That's why here we don't even have that k anymore, because the one dimension we have integrated out, and this is equal to minus theta at minus k. Okay, so that would be the general relation that inversion symmetry enforces on the Wilson loop spectrum. Of course, are all modulo 2 pi, and now that means for our case. So we only have one theta. We don't have a k dependence anymore. There's only the kx that we integrated over. For our case, this means that theta has to be either 0 or pi, right? These are the only values compatible with this relation. And so we have examples for both cases. Okay. Now what does that mean physically? So basically, we've heard that this is to do with the Wannier center. So when we look at our unit cell, then for t larger than t prime, basically our Wannier center is sitting in the middle of the unit cell, and for t less than t prime, our Wannier center is sitting somewhere, is basically at the boundary, exactly at the boundary at this other inversion center. And this has an important consequence once we open up the system, because at half filling, because we are obviously we're filling the system halfway, right? If we want to be, filling only the lower band. When you think about terminating the system, you have, always these one-year centers that are situated, that are centered in the middle of these bonds or the unit cell ends. But then at the end, you have kind of the one-year center that you cut in half, right? And what that basically tells you is that at half filling, you will have basically a half charge at the end. Okay? And that leads to this polarization that Ivo mentioned yesterday, right? So the polarization is then 1/2 basically times the length of your, or the dipole moment is 1/2 times, let me say d for the dipole moment, is 1/2 times the length of your system, plus minus, of course, because you kind of, it's only modulo 1, that statement. So is that now, what is the role played by symmetries here? So we found out that there's this polarization which is quantized by inversion symmetry. But now all of a sudden I'm talking about an end state, and you might think, oh wait, this is topological, right? It's a topological end state. But for that to be true, we actually have to invoke chiral symmetry. So there's basically two things that we have to carefully distinguish. One is the quantized dipole moment in the bulk, which is quantized just by inversion symmetry, and the presence of an end state. And that end state is immediately clear if, again, in this limit t equal to 0, t prime, not equal to 0, we have an end state, and it's entirely localized on the last side, right? So that we have this situation in the Schrieffer-Heger model, and it keeps going in this direction. But there is this state that operator is not in the Hamiltonian, right? So this state is at 0 energy, okay? So basically, if I want to, this is a state exactly at 0 energy. But what protects it from being at 0 energy, moved away from 0 energy? So inversion symmetry doesn't do that because the end of the system breaks inversion symmetry, right? So I cannot say that inversion symmetry protects this state at 0 energy, exactly in the middle of the gap. What can protect it is the chiral symmetry, okay? So remember that the chiral symmetry is sigma 3, right? So it acts like plus on this last side. So this thing is an +1 eigenvalue, eigenstate of C. And so the spectrum of the whole chain would basically look like some bulk stuff. Then there is this end state, and there is more bulk stuff. That would be the energy spectrum of this whole chain. And all these states in the bulk, with respect to the chiral symmetry, they are not eigenstates, right? Chiral symmetry maps any state here to a state up there, and so on. An eigenstate of C I can only find at 0 energy if it's supposed to be localized, and so here I have found one. It's isolated, locally isolated, and everything else is gapped near it, and so it cannot move it away as long as I preserve C. Okay. So that's the important distinction, basically, that we have to be aware of. The distinction between the bulk dipole moment being quantized just by inversion symmetry and the fact that there is a topological end state, in this case the Schrieffer-Heger end state, which is protected by this additional chiral symmetry. Okay. Now, that was the discussion of 1D. Maybe another, let me see. How am I doing with time? So are you talking about one dimension? Yeah. Okay, so in one dimension you always have to have a spectral symmetry to protect an end state. It could be a particle-hole symmetry or a chiral symmetry. But a topological state in one dimension always, or even in general, is sort of a zero-dimensional topological state, always needs some spectral symmetry to be protected. In the superconductor, it could be a particle-hole symmetry, but yeah. Because in 2 dimensions, you have spectral flow, right, like in the quantum Hall edge, but here you don't have that. And so to pin a state at a specific energy, you need a spectral symmetry.
What did you see that there is one state that is localized and which state is that?
So you see it basically from this drawing. So suppose, so the Hamiltonian in this limit is only consisting of terms that hybridize this side with this side and this with this. So this last side, or this operator, is not acted upon with the Hamiltonian, okay? So this degree of freedom, this in the Hilbert space here, is the Hamiltonian doesn't act on it, so it doesn't cost energy to either populate it or not populate it. Okay? So that is one sort of single particle level that's sitting just at the end. And now I can make a perturbative argument. Once I've established this in this specific limit, I have this eigenstate of eigenvalue +1 of this chiral symmetry at the end. Now, if I change the Hamiltonian, preserving the chiral symmetry and preserving the spectral gap, this, by spectral continuity, the state has to stay there, right? So I can now say, okay, this is my diagram for t equal to 0. Now I switch on t and draw what happens to these energy bands. Well, they can wiggle a bit, but as long as this gap is retained, this state has to stay there, because of chiral symmetry, because it's an eigenstate of chiral symmetry. If it would go up in energy, for example, or go down, the chiral symmetry would be broken, because it's a spectral symmetry, right? But did you understand why this state is there to begin with? Like putting an electron here or not putting it is the same energy, because it's not in the Hamiltonian, this operator. Yes, yeah. So now, well, I have to know. So the Wilson loop gives you the polarization in the bulk, and whether that polarization corresponds to a topological end state depends on whether you have the chiral symmetry or not. So it's a question, you need to know what symmetries you have to interpret correctly the Wilson loop result. Okay, cool. Now let's go to 2D. So in 2D, we have the spectral flow. We have churn insulators, as we heard yesterday. And I just want to sort of tag onto this a little bit. So we are looking at a two-dimensional system which displays which is supposed to display a quantum Hall effect. So this two-dimensional system I conveniently wrap already on a cylinder, and I pose that it has a Hall conductivity sigma xy equal to E squared over H times a churn number C. Okay, that's what we learned yesterday, and now I know that if I wrap it on the cylinder, the momenta, if I use periodic boundary conditions, are given by 2 pi over the length of this, or the circumference of the cylinder, times n, where n is integer. But if I insert a flux in this system, pi, then this changes the boundary conditions. After an electron going once around, it picks up this extra phase. So this is for periodic boundary conditions. And with phi twisted boundary conditions, then the allowed momenta are 2 pi over L times n plus this flux phi over phi naught. Phi naught being the flux quantum, right? And so this is now a k that depends basically on n and phi. Okay, ky. That depends on n and phi. And so now I can ask myself, what is the charge that is transported, right, from here to here when I do a full flux insertion? Well, this is supposed to be the Chern number, but how can I compute it? I can basically look at the position of each electron, right, and I can ask, like, by how much, if I integrate the position along the x direction, how much current is going through the system in this, as I twist phi from 0 to 2 pi, okay? So this is a way to count how much charge I get. So so we already figured out that the position is this, is the theta, right? Our eigenvalue of the Wilson loop at ky that now depends on phi and n. And then I have a certain number of those eigenvalues maybe that I label by j. And I have to sum over all these j bands. And then I want to, so this is the position, so the current will be the phi derivative of this integrated over all phi from 0 to 2 pi. Okay, and then I also want to sum over all these electrons that I have. So I have 1 over L times sum over n electrons. So this would be the total charge, right? So this again was our position eigenvalue. So now I can ask the total charge that's pumped, and so if I have to sort of transfer this integral from phi to an integral over ky using this formula, and what I obtain then is sum over j integration from 0 to 2 pi dk y theta of ky j dky over 2 pi, and this has to be equal to my Chern number c, right? So basically, this is another way of relating the position to the whole response, and this again, in the case where there's only one band, right? This was the integral over kx of a of x, right? You remember that? So that was the eigenvalue of the Wilson loop, and that is now. Basically, I forgot the ky. Sorry, this should be partial ky. Okay, and now you see that that I basically have half of the formula for the Chern number already. So it's the part that I have is partial ky a of x integration of d2k. Okay, but this is not a gauge invariant expression, and we saw yesterday the gauge invariant way to complete this would be partial kx ay. So the reason why this basically doesn't appear to be gauge invariant here is that I've chosen a specific gauge that where all the winding is contained in this one direction, and the AY is basically not winding in this specific gauge that I use for the Wilson loop. But so basically, in all generality, of course, I have to write something that's gauge invariant, and actually now I can also give you the non-abelian version, which would contain a trace here. Okay, So that's for all these different eigenvalues J. Okay, so that's the Chern number of these bands. But now how do we actually sort of pictorially understand this? So we have this ky, it goes from 0 to 2 pi. And now in the x direction we have all these unit cells, right? So 0, 1, 2, and so on. And suppose we have only one occupied band, then you know, we have the same position eigenvalues or Wilson loop spectrum at 0 and 2 pi, but for this winding to be sort of, you know, give us some non-trivial Chern number, I cannot just connect them like this, right? Then this winding number would be 0. But for example, to get a Chern number 1, I have to connect them like this, right? And so on. So that is how basically the charge gets pumped from one side of the cylinder to the other side of the cylinder. And now it's kind of already a little bit suggestive, because I think everybody of you has seen a Chern insulator or quantum Hall band structure sketched like this, right? I guess everybody has seen that before, where this is meant to be the energy, this is the momentum, in our case, and the ky momentum, and so there is a state that's flowing, an edge state, right? That's flowing across the spectral gap in the bulk, and so this looks somewhat familiar, right? If you turn this around, the only problem is that here are so many more bands, and here we have basically the bulk and only one traversing one, and in fact there is a very strict relation between these two things. So the one being the Wilson loop spectrum, right? That's essentially the Wilson loop or the projected position operator spectrum, and that's the energy spectrum of the system. And I'm not sure whether I have enough time. How much more time do I have? 0. Okay. Okay. Then I might. Okay, I'll do this in the next lecture then. Okay, so then we'll start next time with sort of making this a little more rigorous, this connection between the Wilson loop spectrum and the actual edge spectrum, which is basically showing that the Wilson loop spectrum corresponds to the boundary spectrum, or as a 1-to-1 corresponds to the boundary spectrum of a topological system. Okay, so questions for that part so far? Yeah. Yeah. So you're.
So I'm saying that for 1D case, we also have the winding number as a topological number.
Yes.
Which is very much like
It's basically the same thing, yeah.
well,
so okay, there's two things. The winding number is actually a little more powerful than the Wilson number in this case, because it's the Wilson eigenvalues are only modulo 2 pi defined, right? The winding number takes advantage of the chiral symmetry, and for that it's an integer. Well, the non-abelian nature, I think we'll see an example later today where the non-abelian nature is really key. For here, for this one, of course, the non-abelianness is really not playing a large role, because you are basically just summing over all the occupied Wilson bands. So these bands are all sort of counted the same, right? I mean, you could have, if you had now 2, then you could have another one that does this also, right? And then the Chern number would be 2, right? Or by the way, another way of getting a Chern number 2 would just be with 1, right? That goes by 2 unit cells, right? So you have a picture like that. That would also be Chern number 2. But yeah, so here the non-abelianness is not so important. It's just to keep the theory general. But we'll have an example later where it is important.
Maybe I have one. So these topological invariants, they are there are ways to calculate them, and they are all equivalent. They lead to the same result. But what would you say is the advantage of this Wilson picture, and when it's the more suitable?
So it's useful if so it's really useful for numerical computations. A lot of the invariants that you see. So here you saw that there is a derivative in this Wilson loop. But it's actually, I wrote the formula with the projectors, and you can just plug that in a computer, and you don't have to take care, for example, of having a smooth gauge or something like this. Many other invariants require taking derivatives, and this is usually numerically not doable, because if you don't have a smooth gauge, you cannot take a sort of a discretized derivative of a Berry connection or something like this. So the advantage of the Wilson loops is really a practical one. In that sense. But it's very important if you want to, if you have a Hamiltonian or a real material and you want to know whether it's topological or not, this is much more convenient to calculate than many other things.